Hello, this is Samyak Agrawal and this is my presentation for project 2 of science 1. So let's look at the problem statement first. So we have to analyze the motion of two pendulums that are connected to one another and are under the action of gravity. So this is our first bob and this is our second bob. The theta 2 is the angle which the second bob makes with m1 vertical, and theta 1 is the angle that m1 makes with the vertical. So this length is y1, this is y2, x2, and x1 and this is x, this should be x1 and this is x2, and x1, x2, y1 and y2 are defined here. So we can solve this problem with the Newtonian mechanics, but it will be very hard to do so, so we'll use the Lagrangian mechanics. So first, the Lagrangian value is T minus V, where T is the kinetic energy of the system and V is the potential energy of the system. So obviously the kinetic energy of the system will be half m1 v1 square plus half m2 v2 square. Now plugging in these values into this equation, we get T equals to this. Similarly, V will be m1 g y1 plus m2 g y2, and plugging the same values of x1 y1 and y2 into this equation, we get this. So the value of Lagrange is T minus V, which gives us this. So first we differentiate L with respect to theta 1 dot, we get this, and then we again differentiate this with d by dt and we get this. So and also dl d theta 1 equals to this. So we did this because we know that by the Lagrange equation, del L by del theta 1 equals to d by dt of del L by del theta 1 dot. So putting in the values, we get this equation. Similarly, we do the same thing for theta 2 and we get this equation for theta 2. So as you can see, this is a second order differential equation. So what we need to do now is we need to solve this equation like any linear equation. So let's suppose that theta 1 dot is omega 1 and theta 2 dot is equals to omega 2. That be the angular sheets for this for the two bobs. Now solving these two equations and getting omega 1 dot and omega 2 dot out of them, we get omega 1 dot equals to this huge equation and omega 2 dot equals to this huge equation. Now so we have a total of 4 differential equation in terms of theta 1 dot, theta 2 dot, omega 1 dot and omega 2 dot. Now it's not really possible to solve these equations or get any closed form of these equations. So what we do is we use another method or approximative methods to solve these equations numerically. So one of the methods is Runge-Kutta method. So let's see what happens in the Runge-Kutta method. So in this method, we suppose that there is a function of t, and the t is time, and q state variable, and q dot, which is the time derivative of the state variable q, is equals to a function of time and the variable q. So now what we do is we define an initial condition for q, and then we use the recursive formula for qn plus 1 to analyze the equation. So qn plus 1 is qn plus h by 6 of a plus 2b plus 2c plus d. So here h is timestamp. So in this method, we don't consider time to be continuous, we rather consider time to be we consider time to be distributed according to h, which is the time step. So here h is the time step. So if we suppose that at time t equals to tn, our state variable in state q, the state variable will be in this state qn plus 1 when the time becomes t of n plus h, and the values of a, b, c, d are these. So we'll just use these are just the approximative values used. So what we'll do now is we'll use sorry for the pause. So now I'll demonstrate how chaotic the system can be depending on the initial values that you take for theta 1 and theta 2. So for this particular example, I've taken theta 1 equals to 3.14, theta 2 to be 0, omega 1 and omega 2 to be 0, and in the second part I've taken theta 1 to be very close to 3.14, that is 3.12. So we'll see how theta 1 and theta 2 change with time depending on what the initial condition was. So yeah, so this is how theta 1 changes depending on the initial condition. So initial condition in the first part is I've taken theta 1 to be 3.14 and in theta 2 to be 3.12, so they start off very similarly, and as we see, the graph are more or less the same. There are just one or two places in the graph where you can see a real difference based on what the initial conditions of for theta 1 was, and but when we see the graph for theta 2 is here, you can see the graph for theta 2 is very very unpredictable. They start off similarly, but after that they kind of go their own way depending on what theta 1 and theta 2 was, and here you can see that the difference is not that big in theta 1, but still theta 2 with respect to time changed quite differently from one another. So in the end, as you can see, there is a huge difference between theta 2 values considered depending on what the value of theta 1